Okay, so let's look at the few ways to blow up the model. Okay, so some of you know that the SCHISM, either 3D or 2D, there is quite robust. You know, it's quite resilient to lots of issues. But you know, there are a few ways to actually blow up the model. You know, besides the gross errors. Okay, some of them are related to numerics. Most of them are related to the physics. So the first one is a violation of inverse CFL. So SCHISM is an implicit model, so we do require this kind of inverse CFL criteria. Um, and the second one is you accidentally block out some of the major channels, so the flow cannot go through. In extreme cases, you know, you can blow up the model. And the third one is, and some instances, some open boundary segment become dry entirely. Okay, entire segment becomes dry, and you happen to impose a velocity boundary condition there. The code doesn't know what to do; it will crash. The fourth one is related to the bad quality quads used by the mesh. So if you want to use quad, make sure the quality is sufficient. There's a preprocessor script you can use to easily check and fix these issues. So it should not happen. The fifth one is related to the use of large drags in shallow regions for 3D cells. So this is by far the most common cause for crash. Okay, so if you see noisy, wetting and dry near the shallow regions, you um, you probably should suspect that this is a cause. Okay, so there are a number of ways to remedy this. I will talk about in the next couple of slides. And the next one is basically related to the improper use of some combinational parameters. For example, you don't have sufficient amount of viscosity to stabilize the momentum equation, so that could cause the model to crash. And the another example is that you have lots of very complex domain and lots of cores, and then inter-subdomain backtracking crash because some dimension of arrays is exceeded. So this is purely related to the memory issues, nothing to do with accuracy. So you just need to increase some dimensioning parameters. So this can happen for very large complex grid in combination of large core counts. So in any case, you know, if your model crashes, if your SCHISM crashes, don't panic. Visualize the surface velocity in animation mode to try to find the potential issues. Usually it's pretty obvious, okay? So I will not talk too much about how to calibrate the SCHISM 3D. So this is a very um, long story, and lots of this kind of steps are also related to your experience. You need to understand how the model works. Okay. So, but you know, I just want to mention a couple of very, very high level and important points. And you should always remember that the mesh is the single most important factor for accuracy for unstructured grid models like SCHISM. Okay. So there, so in other way, in other words, the scale of the SCHISM 3D is closely tied to the mesh quality sometimes. Okay, so model is forgiving for very skewed elements, but if you want to get um, very, very good results in certain regions, sometimes you probably have to modify the mesh. Okay. And the good news is that if you master mesh generation for 2D, then you are more than halfway there. Okay, so there are some extra steps I will talk about. But just remember, you must be willing to go back and revise your mesh because for unstructured grid models like SCHISM, so this is one of the most important handles. So I will not talk about the other 3 points because for this specific project, we don't really expect you to tune other things. You just follow our steps and using our existing pre-processing scripts. So you should be able to do a good job. So let's look at some high-level details about grid mesh generation. Okay, like I said, the mesh is the most important factor for unstructured grid models. So you should always keep the mesh generation process reproducible and repeatable. We use SMS, we keep the map files and DM sources, and whenever we have a need, we always go back to those sources and redo the mesh. Okay, because the accuracy and sometimes performance depend on the mesh. So you know, the worst case scenario is then they just get a mesh and tune the parameter to death, and you still couldn't get what you want. Okay, so just remember that. And they always keep everything workflow repeatable and reproducible. And as far as mesh generation for SCHISM 3D is concerned, the focus should really be to resolve the key features. And you do not need to worry too much about the instability. So here is an example of resolving the features. Okay, so this example is taken from one river in China where the tidal velocity can be very, very large. And you can see in this part of the channel, the channel width is very narrow. It's about 20-meter-ish. Okay, so, and if you do not resolve this channel, imagine, okay, you have a very strong flow before that. Okay, so the most of flow will be reflected back, and part of that energy will be used to try to inundate the upstream dry cells. So that may crash the code sometimes. Okay, so in this case, always remember to resolve the main channels, and don't be timid in resolving the narrow channels, because the model is implicit, it will not blow up. Actually, the converse is true, in a sense that if you do not resolve this the narrow channels, the model actually may crash. Okay. And just refresh memory from mesh generation for 2D. Again, you know, mesh smoothing is not required, and resolving features is much easier with the SCHISM because of the implicitness factors. And the skew elements are fine in non-eddying regimes. Okay, so in a near shore, estuary, rivers, watershed, you are allowed to use very skew elements. So when you do mesh generation for either 2D or 3D, always keep this table ready. This table is basically generated by the inverse CFL criteria. So for SCHISM, we require CFL number not to be too small, meaning greater than 0.4. Okay, CFL number is defined by this, right? So you notice that we added this particle velocity to the wave velocity. This is because in the watershed, this square root of GH is undefined because H is a negative. So in those regions, what matters is the particle velocity, and we can use a characteristic velocity of 1 meter per second as a reference. So this table is generated by assuming a very conservative minimum time step. Okay, again, you know, SCHISM's requirements are often opposite to requirements by other explicit models. Just get used to that, okay? Because this is very different types of models. So when we talk about the CFL, we usually talk about the minimum time step instead of maximum time step, because the larger the time step, the larger CFL, right? So in theory, that should make the model very happy. So assuming a very conservative minimum time step of 100 seconds for most typical field applications, the mesh size should not be finer than these numbers. Okay. Again, you know, this is opposite for many other models. You know, you can go finer, but you may not go coarser. Okay. So at depth of 1 meters, you may not go coarser than 800 meters. Okay, and 10 meters, the mesh resolution cannot be coarser than 2.5 kilometers, etc. And so you use this table as a guide when you do mesh generations, and in map projection, so everything is measured in meters, that's fine. But you can also do mesh generation non-net for large business scale grid like a Pacific. We like to do it in non-net. Okay, and then you need to do some estimate to convert the degrees to the meters. And SMS can actually tell you that you can measure distance in meters inside the long net map. So again, remember CFL cannot fall below 0.4. That means if you refine the mesh, you are fine. If you coarsen it, you may not be fine. So you need to remember to recheck the CFL. Similarly, when you increase time step up to a certain minute because of the truncation error, right? If you time step becomes too large, your truncation error eventually will catch up with you. But in general, increasing the delta t, the time step inside schism is fine. But when you decrease time step, you need to be very careful. So this is another very common mistakes by users who switch from an explicit model. Okay, so they always think that the decreasing time step will enhance the model stability. You know, but for schism, that's not always true. Okay, when you decrease the time step to below certain point, when the CFL starting to fall below 0.4, anything can happen. The model even may become unstable. So just remember that if you have to, for whatever reason, you have to decrease the time step, you may want to consider refining the mesh to satisfy the inverse CFL. And like I said, in the watershed, square root of GH is undefined. So in those places, you should remove this square root of GH. So let me, in those places where H is negative, you can actually set a minimum depth of 0.1. So why? Because square root of 10 times 0.1 is 1. So that basically take place of the particle velocity. So now let's let me show you how to do this in GREdit. So let's look at this grid and check CFL. So you notice that I already projected from longland to CPP because I want to measure everything in meters, right? When you check CFL, you have to check that in a projected space. So to check CFL, first of all, impose a minimum depth of 0.1. So this way you basically impose a minimum depth of 0.1. And then after that, you go to special dimensionless numbers and input a time step of 100, the minimum time step of 100 seconds, and 0.4 as the warning value, and depress this display field accept. So you should be able to see this. Okay, now you see this CFL. Okay, green means it's bad. Red, it means it's good. Okay, larger, red means larger than the 1, CFL 1. The orange is between 0.4 and 1 is also okay. So you can see that most of the violations happen in the shallows, right? So if you use 150 as we did for this application, you should be able to see most of them are gone, right? And in this region, you know, it's a watershed, so it doesn't matter, you know. As long as you don't see this kind of large green patches in the deeper water, you know, you are usually fine. Again, here, you know, this is a watershed, so it's fine. So the schism mostly uses implicit solvers. So the only explicit part is the horizontal transport solver. Okay, so that's the schism's main bottleneck, as you could imagine, because implicit, bypass most of the stability constraints, so it's very, very efficient. Whereas the explicit solvers, you may bump into the efficiency issues. So when you do mesh generation, sometimes you need to consider that. Just remember horizontal transport solver is still explicit. So if you have a horizontal mesh resolution very, very high, and your velocity there is also very high, you can cause excessive subcycling for the transport solvers. So there are ways to get out of this kind of efficiency bottlenecks. For example, you can use upwind, which is much more efficient, or you can even in the extreme cases, you can fall back to the EOM, which is unconditionally stable. Okay, so there are ways you can get around this. For example, this is a mesh we generated for San Francisco Bay and Delta. Inside Delta region, you have lots of very fine resolutions, couple meters, right? So, in order to alleviate the bottleneck of the transport solvers, we basically declare all those shallow delta regions to be the upwind zone. So the only extra step you need to take when you generate the mesh for SCHISM 3D as compared to 2D is that you really need to pay attention to the eddying regimes. Okay, so eddying regime and non-eddying regimes are governed by very different physics. For example, the non-eddying regime, the near shore, is mostly forced, okay, and dissipated because of bottom friction and because of the boundary condition and the geometry. So in other words, the processes near shore in a non-eddying regime are ageostrophic. Whereas for eddying regime, it's weakly forced, mostly balanced regime. Okay, so the geostrophy is the dominant balance there. So when you try to do the mesh generation, you need to try to preserve this geostrophic balance by using gradually varying mesh resolutions. This is also because the bathymetric slope in the deep ocean is negligible, right? The variation, is negligible. And if you use very sharp mesh transitions in the eddying regime, you can distort or create spurious eddying processes. Okay, I must emphasize that if you do this, you will not blow up the model. You will survive, but you see some spurious processes like upwelling of cold water in the middle of the oceans, etc. That's because you are distorting the eddying processes. So as a result, we always advocate when you do mesh generation for 3D in the eddying regime, try to start from simple. Okay, always start from simple design. Do not over constrain the mesh in the eddying regime by using lots of arcs there. So having said that, the particularly challenging is the mesh generation for the transitional regime between the eddying and non-eddying regimes. So for example, in the Pacific, you have lots of tiny little islands sitting on a very steep bottom slope. Okay, so most of the model will misbehave on a very steep bottom slope, right? And you combine that with a then very steep bottom slope with a very fine resolution you want, and those islands, you can imagine that the problem may occur, right? So our advice is stick to the simplicity rules and only add auxiliary arcs when necessary. So in this way, you allow mesh to organically transition smoothly in the eddying and the transitional regimes without distorting the eddies. Okay, so the way you find out if you have a problem is by looking at those spurious upwelling patterns, very cold water in the deep oceans. Okay, so usually this kind of spurious upwelling process happens within a couple of days. They are very easy to spot because they always persistent no matter winter or summer. So they should look different from true upwelling. Okay, so As a rule of thumb, if you use about 3 km resolution and islands, you're okay. 1 to 3 kilometers and islands, you're probably okay, mostly okay. But when you start using 1 kilometer or finer resolution and islands, you need to be careful, especially if the local bottom slope is steep. When you end up with a very fine mesh resolution in a deep ocean. Okay, so you are basically teetering on the edge of hydrostatic and non-hydrostatic regime, because your vertical scale is now comparable to the horizontal scale. Okay, your vertical depth is 1 kilometer, your horizontal resolution is also 1 kilometer. So here is the example of what I just said. If you use this, so suppose this is a island you want to resolve. If you resolve with 3 kilometer resolution, right? So away from this island where the deep ocean is, your resolution is still relatively close, right? So this is a 500-meter isobars. Whereas if you use a 1 kilometer resolution and local bottom slope is steep, what happens is that the 500-meter isobars, the mesh resolution is already too fine, okay, already comparable to the vertical scale. So you may have a problem there. So in this case, it's better to add another additional arc in the deep ocean to force the grid to be coarser there. Okay, so you may ask, is there a way, if I really want to do this, is there a way out of this? Yeah, there is a way actually in SCHISM, but I will not confuse you more for that kind of tricks. But for now, just remember, if you have a tiny island sitting on a very steep slope, be careful when you use a very high resolution. Okay. So here, this example is taken from the Caribbean, the Bahamas, right? So those islands are all sitting on very steep slopes. So in between those islands, you have eddying region, that's deep ocean, right? And around those islands, you have non-eddying regimes. So how to generate mesh for this kind of complex geometry, okay, with steep slopes? The way we did is we use a number of auxiliary arcs, basically delineate between eddying and non-eddying regimes. So basically, the main purpose of those arcs is to ensure that the mesh resolution is not too fine in the eddying regimes. Okay. And inside eddying regime, we do not use any auxiliary arc. We allow the mesh to organically, smoothly transition inside that regime. So in this way, we keep all the sharp transitions in element size inside the non-eddying regimes. So if you look at the final grid, it looks like this. In the eddying regime, you see very smooth transition of the element size. Inside the non-eddying regime, shallow regime, you have some skew element coming out, which is fine, right? Like this kind of skew element, which is fine. So on the other hand, if you over constrain, if you add some arcs in the eddying regime as well, over constrain eddying regime, as a result, you get some skew elements coming out. You see this kind of spurious upwelling. Okay. So the cold water in the deep oceans. After a mesh is generated, you can use GREdit or SMS to generate the land boundary and open boundary segments. I will not go into the detail, but this is something we covered for the 2D. So just remember that when you designate the land boundary and the open boundary, make sure they dovetail with each other tightly. Okay, leave no gap between the open boundary and the land boundary segments. If you do, then you will get an error saying that a broken ball. Okay. And after you generate this boundary condition part, you need to remember to append this boundary condition part to hgrid.gr3. Okay. And this is, if you use gredit, you can also easily check the very skew and very negative elements. Of course, if you have a negative element, the preprocessor will definitely tell you, you have illegal elements. So let's go back to here. If you go to status, okay, it will tell you if you have any negative. You see a small minimum element area is 7.3 meters, so which is fine, right? Still positive, and maximum is this number. So if you have a negative number here, you may have a problem. No, you definitely have a problem. Okay, so after you get a good mesh, you pass a preprocessor and the mesh is accepted by SCHISM, then you need to set up, uh, I take them back, when you get a mesh, then first thing you want to do is use SCHISM's preprocessor to check mesh integrity, right? Start from simple, always check the mesh first with a 2D model with a preprocessor on. This is a preprocessor to find any grading errors. So for this step, to check the mesh integrity, you only need three. You only need four inputs. That's hgrade.gr3, vgrade. You can use a very simple 2D configuration, right? And param.ml, of course, that's the main configuration file, and your choice of button drag. For 2D, we typically use a manning, and for 3D, we typically use drag. And inside the param.ml, you can basically use a barotropic flag without the transport solvers to basically bypass most of the other optional inputs. And for time step, for field scale applications, we always start from 150 seconds. Somehow it's a magic number. Always start 150 seconds and just from there. And then you need to run the SCHISM preprocessor, and if there's grading errors, you will see this outputs fatal error. Okay, they will tell you. For this step, you do not need to have correct open and land boundary segment specifications. You can, for example, use no open boundary at all, just two land boundary segment dovetail to each other, right? So after you pass the preprocessor, then you can proceed to set up the model in 2D or 3D. We recommend you start from 2D because it's much simpler. Okay, to start to set up the model, just remember a few things. Remember few ways to blow up the model, right? So one of them is make the entire open boundary segment dry during simulation. If you also happen to impose the velocity boundary condition there. Okay, so for that, okay, we have a couple of devices for you on how to impose the river boundary. Okay, so river boundary is where the boundary segment, entire segment, could potentially become dry, right? Especially you go to upstream rivers, the river bottom is already above your datum. So how do you impose the rivers there? There are a couple of ways. First way is to locally dredge a small section to feed in the river flow. Okay, so this local bottom now is below the datum, so you can easily feed the water there. Or you can use source and sink. This is the most robust option, right? So you can basically inject the source and sinks locally anywhere. It doesn't have to be the bottom, anywhere. Okay, inject the river flow this way. And there are other fancier options and more accurate options I will not get into. And just remember, if you impose river boundary condition as open boundary condition, okay, you inject the river flow using the open boundary segment option, you need to use negative values for inflow. Okay, so this is very confusing, and this was done because of historic reasons. Now we can change it, but you probably create more confusion. But if you use the source and sink options, you need to use positive values for source. Okay, they are just opposite. Okay, so here are some details in setting up the 2D model, which is quite simple. You use 2 levels in vgrid.in. So this is what the vgrid should look like, right? So the magic flag 2, it's SC flag. So you use a very large maximum depth between S and Z to cover all maximum depths. So don't change this. And you also ensure that the HC is large enough, because when the local elevation, surface elevation falls below the negative value of this number, model will crash. Okay, for example, if you have a tsunami, you may have like minus 30 meters elevation, when during the withdrawal phase. So in general, 100 meters is pretty safe. Okay. And just remember, mesh is the most important handle to tune, and other parameters include the boundary condition, bottom friction, Manning's N, or sometimes the surface drag formulations. Okay, so this is probably the most common problem of setting up the 3D, okay? Meaning you are using a very large drag in shallow areas, wetting and drying areas in 3D regions, okay? Just remind you that the SCHISM allows polymorphism. That means you can mix 2D and 3D and 1D in a single grid. Okay, so but if in a shallow you happen to use 3D vertical grid, and you also use a large bottom drag, you may have a problem. Why? It's very simple. In a 2D case, you don't have a problem because you only have 1 degree of freedom in a vertical, right? So if you increase the drag, you will immediately slow down the velocity. Whereas if you use 3D configurations, if you increase the drag in a large drag in a shallow region, you basically exacerbate the vertical shear, right? Because you still have vertical degree of freedom to play with. So that's why you get this kind of very ugly and large and noisy velocity coming out in the shallow regions. So how to fix that? First of all, the best way is to use locally 2D configurations, take full advantage of the LS square, okay, polymorphism. So this is the best approach. Okay, so you basically revert to this kind of 2D, locally 2D configurations. So you can impose a very large CD. If you have to use a 3D configuration in shallows, then you should set a small CD. Okay, so again, this is a completely counterintuitive. Okay, so this, but I'm already explained to you what this means physically. Okay, so you are basically trying to alleviate vertical shear by using a small CD there, or you can even use zero friction. The model is completely stable, no problem. Okay. Okay, so there are many other details related to the 3D model setup. So I won't have time to go through all of them. Okay, here are some important ones related to the Pacific project. So mesh generation we covered, and in terms of time step, always start 150 seconds. That's a magic number. For bottom friction, start simple, use a constant drag, okay, 0.025 default drag. So this way, if you happen to use 3D configurations in the shallow, you should not have a problem, okay? Whereas if you use bottom roughness, in the shallows, you usually get a very large CD coming out. It become a problem. And try to design your vertical grid using the LS square, using 1 layers in the shallows to alleviate this kind of pathological cases in 3D. Okay, so we have the Fortran script for you already. So just use that. It's already using this kind of polymorphism. And in the Pacific project, we also give you a Fortran script to allow you to use a variable drag, okay, CD, right? Especially when you go to shallows, you probably really want to increase the drag in the watershed. You can do that. Just remember, always remember to check the locally 3D regions in the shallow. Okay, make sure that you do not use a very large CD there in those scripts. For occasionally for cases with very violent wetting and drying processes, okay, you need to we always recommend you using the fully implicit mode, implicit factor of 1 to boost the stability. So this is works very robustly. And we will, in the next part, I will talk about pre-processing and post-processing. So we'll go into the details of how to use HiCon to generate the initial conditions and boundary condition and tracer margin inputs for SCHISM. So if your HiCon inputs of sufficient quality, usually this step is very robust. For atmospheric forcing, in addition to the air used in 2D, now you need two other types of atmospheric forcings called rand or radiation fluxes, and PRC, that's precipitation. Okay. And just remember 3D now you have a complete physics. You can ask a model to calculate the evaporation for you. And when that is done, the evaporation will be combined with precipitation as an extra source and sinks. Okay, so this is automatically done in the 3D model. So this is different from the 2D where you have to really convert the rain source into the source and sink. Okay. And for 3D, it's very important to use adequate momentum dissipation, meaning the horizontal viscosity. So we already tuned for you. So use those settings in param.nml. And you need to use generator Shapiro.gr3 to control the viscosity, at different places. For example, near very steep bottom slope, you want to crank up the viscosity aggressively there. Okay, we have a Fortran script for you. Okay, and in addition, you might have to increase the filter strength inside the Shapiro.gr3 around all those high resolution islands. I'll show you example when I talk about the mesh generation for Pacific. And in terms of wetting and drying threshold, that's same as 2D. So 3D works robustly if you use, especially if you use LS square. And the efficiency is important. This is mostly related to the tracer transport. So again, avoid a large number of subcycling for the horizontal solvers. Use lower order or EOM if necessary. So I won't talk too much about the Fortran script to generate the LS square vertical grid. You can read the script through. Basically, there are a number of controls inside this script to control how you want to, what kind of vertical resolution you want to have near surface and bottom in the middle layer if you want, right? And how much degeneracy around the bottom you want to have in terms of shaved cells, and also you have a number of parameters to control the generation of a master or reference vertical grid. So if you read the menu, SCHISM takes different types of input files. Okay, some are ASCII, some others are netcdf files, right? So .gr3, that's the mesh-like files, just like horizontal grid, right? Just remember that the hgrid.gr3 is different from other .gr3 because it has a boundary condition information at its end. hgrid.ll, that's non-land format of the hgrid.gr3. So it's just the XY coordinates are the longitude and latitude. That's the only difference. And the boundary condition .th, you have two types of boundary condition inputs. The .th is basically ASCII input. .th.nc, that's netcdf. Okay, so we use netcdf to conserve the file size. The .ic, that's the initial conditions for elevation and tracers. So those are the ASCII format, and in most cases are actually GR3 format. .prop, that's a GR edit element property format. So they this input basically specifies element-centered properties. For example, you can tell the code which element you want to use lower order transport solvers. So you can use this tvd.prop. sflux is a directory. So this directory contains all the atmospheric inputs. Like I said, for 3D, you need the sflux underscore air underscore rand underscore prc, 3 types. So the netcdf inputs are standard CF convention. The main configuration file for SCHISM is called pram.nml. So it's Fortran name list format, relatively easy to read. And there are two .in files, a vertical grade.in, that's ASCII also, and a bctype.in, which specifies the boundary condition and the title, forcings, etc. And rest of the netcdf files include the hard start, right, initial condition. If you use a 3D variable initial condition, you need to use hard start.nc, and tracer login inputs, and also the some boundary condition time inputs. So it's basically .th.nc. Okay. And the other modules of SCHISM, of course, have their own input files. So like I said, the first thing you do after you get a new mesh is always to check mesh integrity using SCHISM's preprocessor. So to do this pre-processing, you need to prepare some input files, just follow them, hgrade, vgrade, and param.ml and bctype, and your choice of button frictions. Okay, and during this stage, you don't even need to have correct bathymetry and the boundary designations at all. Okay, you can use one layers to set up the 2D for simplicity. Okay, and inside param.nml, you can specify barotropic flags. Okay, to keep everything simple. And BC types in, you can basically specify no open boundary at all. Keep it super simple, and then you need to run the SCHISM executable using one CPU only. Okay, for preprocessor, you can only run with one CPU. If you try multiple CPUs, the code will tell you change it to one CPU. And then you need to check this fatal data error for any fatal errors. If there are, then you need to go back to mesh generation until this is successful. So this is a typical run directory for SCHISM 3D. I take this from Columbia River test, right? So you can see all those input files are here. If you group them into categories, GR3, LLIC, those are the ASCII inputs. And .in, basically you only have two, the BC types and the vertical grid. TH, in this case, we only have the ASCII files, the river input, the flux.th, and the river temperature input. And the rest of them are the netcdf, so hot start, right? Initial condition and the temperature and salinity margins. And if you look at typical output directories, you see lots of files. This is because SCHISM, in general, most of the cases, outputs results per MPI process, okay? So you will not combine the output for you. The raw outputs is per MPI process. So there are exceptions like station output, the code already combined for you. But for most of the outputs, SCHISM outputs per MPI process. So there are post-processing scripts to be used to gather all MPI ranks into a global output, either ASCII or netcdf4 outputs. But for large grid, this can be time consuming. So we are actually moving away from this. Right now, most of our, actually all of our for transcripts and visit, newer version of visit can handle this raw output, uncombined outputs. But if you look at the uncombined raw output, it looks like this. Okay, for uncombined, you always have this kind of MPI rank number, 0002, 4 digits, right? And sometimes it's near the end, sometimes it's in the middle. So this is the MPI process number, and this is stack number. And hot start, again, similar MPI process number in the middle, and last one is time step number. And we have post-processing for transcripts to combine the netcdf outputs into a global output. So after combining, you can see that the MPI process numbers disappear, right? So you only have this stack number left. So this is global output. And similarly for the hard start. And for ASCII, we also have for transcript to combine, for example, the maximum elevation during the entire duration of the simulation into a final max elif.gr3. So this is combination process is very, very quick because it's ASCII. But I must caution you that if you do compound flooding studies with watershed, please do not use this max elif.gr3 because this is because in the watershed compound flooding processes, the transients are a nuisance. So you really need to remove the initial transients, otherwise you get some large elevations. So for that reason, we recommend using this read output 8 to basically specify a starting time to compute the max. So mirror.out is the one, main diagnostic output. So it tells you lots of information when the run is ongoing, right? So the beginning of mirror.out, you see that the run starts at this particular time step, and it will show the domain partitioning information. For example, each MPI ranks will take this many number of elements in the augmented domain, resident domain, and this number of elements in the ghost, and two-tier augmented domain, etc. Okay. And one particular useful diagnostic is this total elevation. So basically, it's a sum of absolute value of all the elevations, right? So if you average them around all the nodes, you get this number in meters. So this can be very useful. You know, for example, if you have normal tidal simulations and this number is 1 meter to start with, you might have a problem, right? You should not start from such a large number. So in terms of raw netcdf outputs, it looks relatively simple. Okay, so the dimensions are related to the local resident subdomain. Okay, it's not the global grid. So that's why you see smaller numbers here. And one thing you notice is that it does not have a collectivity table because collectivity table is centralized in local to global, this outputs. Okay, so it does not have the raw output does not have a collectivity table. And rest of them you can read basically those are the typical output like elevations here, and the coordinates, salinity, temperature, etc. So after combination, the SCHISM output follows the U-grid version 1.0 convention. So one thing you notice that is extra compared to the raw output is the collectivity table now. It's here, right? It's collectivity table. And other than that, you know, it's similar, okay, except now it's all combined. So you can see dimension is much larger here. And the coordinate, we also, by default, is always output there. So you can use this information and each time step to for your own script. So save you lots of trouble to compute the coordinates. I will go through the post-processing and visualization in the next lecture. Right now we have lots of scripts, okay, different type of scripts, Fortran scripts and Python and MATLAB, etc. Um, for visualization, we typically use Visit. So this is the most comprehensive tool for visualization. You can do 3D and you can do 3D slicing, all those fancy things. Another good thing is that it faithfully capture this shaved cell near the bottom. Okay, so and you can do this on raw output or combined outputs. And for MATLAB, it's less efficient than Visit, but can still visualize the shaved cell and combined outputs. In terms of extracting time series, which is a quite a common task for post-processing, um, we have Fortran scripts to do almost everything you want, okay? Vertical slicing, horizontal slicing, and the point, X, Y, Z, T, time series, etc. So when you run the model, you can ask the model to output the variables and some stations, okay? So we call it this online approach. So this is the easiest, but the caveat is that if you make a mistake in station coordinates, you have to rerun the model, which is not always optimal. So typically we use this Fortran script, post-processing script to offline extract the time series from uncombined or the combined outputs. And the interpolation is done in space in 3D. Okay, so this is consistent with the SCHISM code. SCHISM uses linear shape functions. And just be careful that sometimes you get this salinity temperature less than 0, negative values. That's related to the interpretation of wetting and drying. So be very careful if you use our Fortran script, it should not happen. And if you want to do harmonic analysis for the entire domain, for example, your tidal simulations, it's better to use this harmonic analysis modules. Okay. So coming back to this few ways to blow up the model, let's go through them. Okay. And we already talked about a couple of them. For example, blocking the main channel, you may have a crash, or using very large CD in shallow regions. Let's look at other violations. Okay, so this is a very common violation of inverse CFL. It happens when some users try to reuse a mesh from other explicit models. In this case, you can see that you have very large green patches, the violation, CFL violations in a deeper ocean. Okay, so you have a problem. So you need to fix that. You need to refine the mesh there or use a larger time step. And dry river boundary can be a problem, especially when you try to withdraw water from the domain. So this happens in the Bay Delta grid, for example, and this North Bay boundary, we are actually withdrawing water from the domain. And this is the channel there is very narrow. So in this case, if you really want to use open boundary there, you better pay attention to the resolution. Make sure you really well resolve the boundary there to get a smooth wetting and drying. Of course, the more robust way is to use the source and sink options there. So make it more robust. Bad quality quads. This should never happen if you use our pre-processing Fortran script called fix bad quads. Okay. So here is a picture showing some of the potential problems. So you can see those kind of quads. It's the quality is a bit dubious. Okay, you probably should split them into pair or triangles. Okay, so that's what this Fortran script does. It's basically try to pick a diagonal of a quad to split the quad into pair or triangles with a good aspect ratio. So there are other crashes due to the improper configuration. This is related to the physical processes. Okay, so here is one example. The user actually successfully did a 2D simulation for Chesapeake Bay, right? So everything looks nice during storm surge. And then he proceeded to a 3D setup. And all he changes is that the button friction changes because 3D he uses button roughness, which is fine. We checked, and vertical grade is reasonable, right? So when he looks at the results, you can see that there's a large noisy velocity near shore, and you get this kind of very high and noisy elevations and a certain point. So the question is, what went wrong here? So in the end, what we found out is actually related to the physics. Okay, so he basically forgot to use a turbulence closure for 3D. He still uses constant viscosities, and the viscosity value he specified is which is inherited from the 2D model is 10 to minus 6. So imagine when you blow a wind on the inviscid fluid, what will happen? The Ackermann layer will go crazy, right? Because not enough mixing to bring down the wind energy to the water column. So as a result, the surface velocity will become very large. You get this kind of large noisy velocities. Okay, let's quickly summarize what we have learned so far. 3D setup is considerably more complex than 2D, and in many cases, it requires experience and understanding of the physics. But for mesh generation, it closely follows the 2D, but the only thing that is extra for 3D mesh generation is the eddying regime and transition regime. Okay, just make sure that you start simple in the transition and eddying regimes. Do not over constrain meshes there. So in this case, you allow mesh to smoothly transition in the transitional and the eddying regimes. Okay, so you don't distort the eddying processes. And always start from modest resolution, especially at islands. Those islands sitting on steep slopes, 3 kilometers fine, 1 kilometer is probably fine also. And if you have to refine the islands, as you, all of you probably will do, you might need to add auxiliary arcs to delineate the eddying and non-eddying regimes to make sure the main purpose of this kind of delineation is that to make sure the mesh resolution is not too fine in the deeper oceans. Okay. And if a spurious upwelling occurs, again, you won't crash the model. You just see some funny looking patterns emerge. Then you need to adjust the mesh. You know, mostly you need to coarsen the mesh in the eddying regimes. Okay. And after you have generated a mesh for 3D schism, you need to design a vertical grid intelligently to take full advantage of polymorphism using 2D etching shallows. Okay, so if you're not sure, always start from the script we provided you with. And we have relatively mature pre-processing scripts for coupling with HICON and atmospheric models. So as the HICON inputs and atmospheric inputs are not junk, you usually are fine. And remember to set proper moment dissipation, especially by tuning the iShapiro and Shapiro.gr3. So we have a Fortran script to generate the Shapiro.gr3. And sometimes you find the model runs too slow, and you should look at the output for number of subcycles called subcycling.out. And if you find excessive subcycling, you can, there are ways to bypass those. Okay, that's everything.